Hey everyone, welcome back. Today we're going to focus on our third lesson in Unit 4, and that's talking about determining extreme values of a function. Now we've kind of already dove into that in the last lesson when we were talking about critical points, but we're going to go a little bit further and we're going to clear up some maybe misunderstandings, maybe make it a little bit more understandable here. So our focus today is determining extreme values. Now before we get into that, we need to talk about the idea of critical points, or we need to remember it from the last lesson. Critical points are candidates for which we can have extrema on a graph. And if you remember, there were three types of critical points. A critical point occurs when f prime equals 0, when f prime does not exist, and at endpoint. So those are the three places that we get critical points. Now, the important part of that, the important thing that we're looking for is really when the function, when f changes direction. If a function is increasing and then it goes to decreasing, then we're going to have a relative maximum at that point there. So the first thing we have to do is identify critical points. If we look at this graph that's up here, we can see that this function is a strictly increasing function. But we notice that when x equals a, we can draw a horizontal tangent line there, which means that the derivative is equal to 0. Now, if we look a little bit closer, f of a is not a relative maximum or a relative minimum. A is a critical point. A is a critical point because the derivative is equal to 0 at that point. But there is no relative extrema there, because if I look within a very small window around A, the height at A is not lower than all the other points or higher than all the other points, because if we look just to the left of it, we can see values that are below the value that I get when I plug in A, and just to the right of it we get values that are above what I get when I plug in A. So there is no relative extrema here. So in other words, we do have a critical point, but it does not produce a relative extrema. Let's go ahead and take a look at a different graph here. Now, if we look at this graph, we can see that there is another type of critical point. At x equals b, we have a place where the derivative does not exist because we have a vertical tangent in this case. So notice in the first part we had a horizontal tangent. In the second graph we have a vertical tangent, which implies the derivative does not exist there. So that's a critical point. That's a candidate for extrema. But again, what we note here is that there is no extrema. There is a critical point since the derivative does not exist at b, but there is no extrema because the derivative did not change signs. What do we see? We see that f is decreasing right before x equals b, and it's decreasing right after x equals b. So there was no place where the derivative changed signs at that at b. So there is no extrema. So what does that look like? Well, remember last time we talked about number lines. So if I'm looking at the graph of f, the first graph, we have this function that does something like this. And at a, we said that f prime of a is equal to 0 at that point. That is a critical point. Well, when we're talking about the number line would state that we have a critical point at 0. So when x is 0, we have a critical point. We would say that f prime of x, when x is a, we have a critical point. So f prime was 0 at that point. But if we look graphically, we notice that the graph of f, this is the graph of f here, okay, f of x, we can see that f is increasing, which implies that f prime is going to end up being positive. Well, on the right side, we see that f is also increasing. So f prime will also be positive there. So we notice that there was no sign change of the derivative at that point. If there is no sign change on a continuous function, then we would say that there is no sign change on the derivative of a continuous function. Therefore, we have no relative extrema there. If we look at the second graph, again, we saw this idea of a vertical tangent. So at B, we have a vertical tangent. So we would say f prime of B does not exist. Okay, that's another type of critical point. Now, if we're to set up the number line for this guy, we would say at B, for x, we would say that f prime of x does not exist there. But if we check the signs of the derivative, we notice that the function f is decreasing, therefore the derivative would end up being negative. And the function after b is decreasing, therefore the derivative is negative. So again, we have no extrema in these cases. What we notice in the derivative is that the derivative doesn't change signs. If the derivative does not change signs for a continuous function at that point, there is no extrema. And that's very important. That's very important. We have to look at that to determine extrema. We can't just say, hey, find when f prime equals 0. That's where there's a relative max or min. No, you have to check a change in signs for f prime. So let's go ahead and look at the next slide here. Look at this example. Okay. What are the relative extrema? What are the relative extrema of this graph? I'm going to go ahead and put this graph up here. I'm going to see if I can do a good job of this because this is kind of an important one here. Center that a little bit better here. Okay. So it dips down, it comes back up, it comes down, something along this line. Okay, so at -2 and at 2, we have these values here. And notice this graph is the graph of f prime of x. This is not the graph of f of x, okay? There's a huge difference between looking at the graph of the derivative and the graph of the function. So looking at this graph, what do we see? Well, we need to identify critical points in order to identify extrema. Again, keeping in mind that a critical point is when f prime of x equals 0, when f prime of x does not exist, or at endpoints. Okay, so if we look at this graph, again, this is f prime. So we ask ourselves, when does f prime equal 0? Now we get a lot of misconceptions with this idea of f prime equaling 0. I'm going to get a lot of students that f prime equals 0 here and here. And that's not true. F prime does not equal 0 there. The derivative of this graph equals 0 here because there's a horizontal tangent. So the derivative of f prime equals 0 here. But I'm not asking for when the derivative of f prime equals 0. I'm asking for when f prime equals 0. So we would say that f prime equals 0, since this is the f prime graph, f prime equals 0 here and here. Okay? So let me write that down here. F prime of x equals 0 when x equals -2 and 2. Okay? So that's my first set of critical points. My second set of critical points are when f prime does not exist. Since this is the f prime graph, we notice it looks like a polynomial function. There's no place where f prime does not exist. It's a continuous function here. And for the third set, there are no endpoints because this function is continuous. So these are my critical points for f. So now I'm going to set up a number line, and at -2 and 2 for x, we would say that f prime of x is equal to 0 at both of those places. Now, we have to determine the signs of the derivative within the three intervals in between those points. So if I were to look at values to the left of x equals -2, here's where students have a hard time. because they mix up f and they mix up f prime. And if we can get a good grasp of the relationship between f prime graph and f graph, we're going to have a better understanding of calculus and actually end up doing really well. Well, we see to the left of -2, we see two things happening. We see that this function is both decreasing and positive. Well, does that mean that f prime is positive or negative for that interval? Again, f prime is decreasing and positive. This is f prime. So, is f prime positive or negative in this interval? Well, the answer is that f prime is positive in this interval, because positive means to be above the x-axis. F prime is positive here. F prime is decreasing, which would imply that f double prime is negative. We don't care about f double prime right now. We only care about f prime. So f prime is positive in that interval. From -2 to 2, f prime is below the x-axis, therefore f prime is negative. And from 2 on, we also notice that f prime is negative. Okay? So for the graph of f prime, we're looking at f prime here, we see positive values, negative values, and negative values. Now for the graph of f of x, if we were to go backwards now, if f prime of x is positive, that means f is increasing. If you remember the chart that I showed you the other day. If f prime of x is negative, that means f is decreasing. And if f prime of x is negative, that means f is decreasing. So looking at these places here, we would say that there is a relative maximum when x equals -2, since f prime changes signs from positive to negative. Okay? And then if we were to look at when x equals 2, we would notice that f prime does not change signs. If f prime does not change signs, then you don't have an extrema. Okay? So we can state that. No extrema when x equals 2, since f prime doesn't change signs. Okay? So that is the answer here. Now in this case, it's asking us to identify what the relative extrema are. We technically cannot do that here, because to identify what the extrema are, what I'm asking for are the y values. We don't have a function, we have nothing to plug these back into for the f graph, so we can only state this. I guess we could state this. We could say that the relative maximum is f of -2. That's all we can say. And there is no relative minimum. All right. Now, with that said, I do want to go back and compare the idea of an f prime graph and an f graph. So again, this is the graph of f prime. Let me go ahead and draw another graph to the side here so we can compare the differences. So let's say that we have a graph of f prime, and then if we look at the graph of f of x, okay? So now these two graphs are not related to each other. I am not stating that f prime and f here are related. What I'm trying to do is make a comparison between these two things so we understand the differences in what we're looking for here. So let's go ahead and say this was -2, and then this was 2, and this bottomed out at 0. And let me redraw this graph a little bit so it's usable. It'll be the same points where all these things happen. Okay, so This value, this x value is -2. This x value is 2. Okay? And then this one is also 0 here. So that bottoms out in both those cases. So we would say this. We could conclude that looking at f prime, this is the exact example that we had before, the critical points are at x equals -2 and 2 because this is f prime. F prime is equal to 0 here and here. In the graph of f, we're looking at a totally different idea. To find critical points, we have to know when f prime is equal to 0. Again, in that graph, f prime equals 0 here and here because this is f prime. But f prime here is, remember, the slope, the derivative of f. So how do I find out when f prime equals 0 in the graph of f? Well, that's when we can draw a horizontal tangent. So we would say that we have a horizontal tangent here and here. So when x equals 0 and x equals 2, we have critical points on this graph. Because again, this is the graph of f. This is the graph of an f prime function. So you have to understand what you're looking for within each type of graph. So the first question I always ask myself when I'm answering these kind of questions is, what did they give me? Did they give me f? Did they give me f prime? And that will tell me what I'm looking for. If I'm looking for when the derivative is equal to 0 on f, that is where horizontal tangents occur. If I'm looking for when f prime equals 0, but I was given f prime, that's just when the function crosses through the x-axis. So trying to understand the difference between those two things is huge. And so I hope that this clarifies some things and really helps you out in that. Just finishing out that little slide there, we'd say since f prime changes from positive to negative at -2, we have a relative maximum. And f prime does not change signs at x equals 2, so therefore there is no extrema there. So what we're going to do now is we're going to look at a couple more examples of functions and trying to find extrema with those. So still working with the idea of critical points and looking for when the derivative changes signs. So the first one here, we have y equals 1 over x squared minus 1. And so we need to find critical points first. Critical points occur when the derivative is equal to 0 or when the derivative does not exist. So we have to take the derivative of this function. Well, there's a couple ways of taking this derivative. The first thing I know is that this is a quotient, so I can use the quotient rule. The derivative of the top is 0 times the bottom, so times x squared minus 1, minus the derivative of the bottom, so the derivative of the bottom is 2x, times the top, which is 1, all over the bottom squared, so that'd be x squared minus 1 squared. So I'm going to simplify that a little bit. That all cancels out. We're left with negative 2x over x squared minus 1 squared. So that's my derivative function. We have to find critical points. So again, critical points are when y prime equals 0, y prime does not exist, and at endpoints. Okay? So first thing we're going to do is set this equal to 0. So we get 0 equals negative 2x all over x squared minus 1 squared. We can cross multiply to solve this. Ultimately, we end up with 0 equals negative 2x, and therefore x equals 0. So we have one type of critical point when x equals 0. The next type of critical point is when the derivative does not exist. Well, again, the derivative does not exist when the denominator is equal to 0. So we would say that y prime does not exist when x squared minus 1 squared equals 0. So going to solve this, we can square root both sides. We get x squared minus 1 equals 0. Add 1, so x squared equals 1. And then square root that, so we end up with x equals plus or minus 1. So that is another two critical points here, negative 1 and 1. And the last set of critical points are when the endpoints. Well, there were no endpoints to this function, So these are all our critical points. The next step in this process is to draw a number line and identify those critical points within the number line. Now, I do want to make something very clear here. It is never acceptable to just use a number line as justification for why you have extrema. This is just kind of chicken scratch. This is just what's going on in your brain. You're basically writing down on paper what you're thinking in your brain is how I look at it. On the AP exam, if you just do a number line and leave it there, give an answer, and you call this your justification, you're not going to get any points for it. So you want to make sure that you're justifying things with sentences, and you'll see what that looks like in a minute here. And we've actually done it quite a bit. So when x is -1, we would say that y prime does not exist. When x is 0, we say y prime was 0. And when x is 1, y prime did not exist. So those are my 3 critical points there. Now I need to check the signs of the derivative within those intervals, because remember, extrema occur when the derivative changes signs. So a value that's an x value less than -1, if I plug in -2 here to the derivative, if I plug in -2, I'm going to end up with a positive value on top, and then on the bottom I'm always going to get a positive value because I'm squaring my result. So y prime is positive on the left, to the left of x equals -1. If I plug in -0.5, if I plug in -0.5, I'm going to end up with a positive number on top and then a positive number on the bottom. So I get another positive value there. Okay. If I plug in 0.5, well, the top value is going to end up being negative, and the denominator is going to end up being positive. So we get negative values for the derivative there. And if I plug in a value greater than 1, so let's say 2, we end up with a negative value on top and a positive value on the bottom. So we'll end up with negative there. So in order to identify extrema, we have to understand that extrema occur when the derivative changes signs. So when x equals -1, there is no extrema because the derivative did not change signs. And in fact, we would see that the function doesn't even exist there. We have a vertical asymptote. At x equals 0, we have a relative maximum. So a relative max when x equals 0, since y prime changes signs from positive to negative. Okay. And then at x equals 1, we don't have an extrema because the derivative does not change signs. Again, we have a vertical asymptote there. But looking at the derivative, it did not change signs. The derivative did not change signs. So in order to find what the actual extrema is, there isn't going to be an absolute max in this case, because this function keeps increasing. It's a vertical asymptote. This goes up to infinity. Then it starts low again, flattens out, and then goes down. So this is a relative max, but it's not the absolute max because we have higher points over here. And then from here it goes down, and then it starts high again, and then it goes down again. So we have vertical asymptotes there. So we would say that the relative maximum, the relative max, when I plug in 0 to my original function, is going to end up being -1. So our final answer would be something like 0, -1. Okay, it's a local maximum, not an absolute maximum. For the second problem, we have a polynomial. So we have y equals x cubed minus 3x squared plus 3x minus 2. Well, we got to find critical points, so we're going to take the derivative. So y prime equals 3x squared minus 6x plus 3. Okay, we're going to factor this, so we got y prime y prime equals, factor out of 3, so you got x squared minus 2x plus 1 left over. And then we can see that that's a perfect square, so we can say that factors to 3 times x minus 1 times x minus 1. Now, to find the critical points, we're going to set the derivative equal to 0, so we'll set that equal to 0. And solve that. That occurs when x equals 1. And again, if you do not put this line down when you're showing your work on the AP exam, they will not consider this as an answer, or anything else after that really is an answer. You have to show that you knew that there's a critical point when y prime equals 0. Now we're going to look for when the derivative does not exist. Well, the derivative is a quadratic. It always exists. It's a parabola. So this, and then at endpoints. There were no endpoints in this case because there was no domain interval. So this is my only critical point. So I'm going to state that critical point is x equals 1. From there, we set up our number line, put x equals 1 as our only critical point. So y prime is equal to 0 when x equals 1. We're going to plug in values for the derivative on either side of that. Because the derivative cannot be 0 anywhere else, it cannot change signs anywhere else except here. So we're going to plug in, let's say, 0 to our derivative. Well, if we plug in 0 here, 0 times negative 1 is negative 1. 0 times negative 1 is negative 1. So you got a positive times a negative times a negative. That ends up being positive. Okay? Then we're going to plug in a number that's greater than 1. So let's say 2. If I plug in a 2 here and a 2, 2 here and a 2 here, I'm going to get a positive times a positive times a positive, which is a positive. Well, for the graph of y, that means we're going increasing to increasing here. The bottom line is there is no relative extrema since the derivative does not change signs. So we would say no extrema since y prime does not change signs. And that's our answer for that problem there. Okay. So there we go. So that's the lesson today on extreme values. Remember, just as a summary, to find extreme values, the first thing you have to do is determine critical points. Find out when the derivative is equal to 0, find out when the derivative does not exist, and find endpoints. From there, you're going to set up a number line and determine the signs of the derivative on either side of all your critical points. That will tell you the direction of the graph of our function, whatever that is, and we're looking for changes in signs. Whenever the derivative changes signs, that implies that the function changes direction, which means we're going to have a relative extrema of some sort. Again, some things of emphasis: the number line does not count for any kind of work or justification. AP readers are told that when they see a number line to completely ignore it, act like it's not there at all. What they're looking for is words for justification. Okay, so be careful with that. And then I think that's it for today. So I hope that helps you out in your journey through calculus. I'll see you again at the next lesson. Have a great day.